All right, good morning. Physics teachers are awesome, number 91. Today,
Still here, guys.
today, just his physics lecture. I watched the first 10 seconds. It kind of sounds like maybe he's not at his school and is needing to leave some a video for his students. We'll see.
Fedorov here, and again, since the technology couldn't keep up, I'll give you Wednesday's lecture notes now, and I'll send these and have Mrs. Fedorov play them for you, okay? So, hello from Atlanta.
Oh, cool. Okay.
And yeah, there's other folks in the room, but that's okay. They think I'm weird too. So remember we're talking about vectors. Remember we're talking about our airplane and goes here in one direction, wind pushes it in another direction. Let's talk about projectiles now, okay? So imagine that you have a projectile going up at a certain velocity, okay? 10 meters per second. Okay, and actually let's give it a little more velocity, right? Let's give it
So just some comments on the setup. First of all, it's so funny when you look at these situations and you start to think, boy, what if the people in the room interrupt him or something? And then you remember, oh, well, he uploaded it, so it must have been fine. Don't know if there's any edits or anything, or it just sounds like there's a little bit of hubbub in the room, and that's, it can totally hear him and it seems fine. I think that this framing is great. It's very, very likely a phone given the aspect ratio. But man, he's framed up great on the easel. And I'm guessing he has a whole bunch of pages. Well, I wonder how many pages he'll get through. All right, here we go.
40 meters per second, right? Okay, and it's going, let's say it's fired from a cannon. It shoots it straight up. Okay? Boom. Okay? Now, we know it's going 40 meters per second, but we know that at the same point, gravity is pulling it back down. Okay? And gravity, if you remember from the other day, is coming down at 10 meters per second squared. Gravity is an acceleration, so 10 meters per second squared, which means every second it's chewing 10 seconds off of this velocity.
Cool.
So what that means in practical terms is that after 1 second, it's now going, let me draw a little arrow down here to show you, it's going 30 meters per second, and after 2 seconds, it's going 40.
So this for me is an argument to say that the acceleration due to gravity is 10 meters per second. I remember as a student, 10 meters per second squared, just, I don't know. I mean, I could do the units and make them cancel and do all the dimensional analysis and all that kind of stuff, but hearing it as 10 meters per second is nice, and it's something like 22 miles per hour per second, which drives people crazy when I say that, but that really drives home the acceleration aspect of this. Other people like to talk about G in newtons per kilogram, and that's useful for other things when you're doing force and stuff, but I think that the 10 meters per second versus 10 meters per second squared is a really interesting argument, and I actually think that this is a scaffold, right? It's something that we would eventually take away. We wouldn't always say it in our professional lives, but it's interesting to think about how we start with that. And I just love how he's doing this. He picked obviously some numbers that are going to work out really nice for him, right? It's clearly going to be at 0 after 4 seconds. And I think that that's, by rounding the 9.8 up to 10, super useful. It's a, what is that, a 2% mistake? Yeah. So I think that big deal, right? And I think that that's really great. I am curious about how he's going to cram it all up at the top. I wonder if at some point he's going to say, oh, I should have drawn this line lower. But you can see he's already sort of drawn, taken less space here for the second, which also makes sense. It was going slower.
20 meters per second. And so on and so forth, until eventually, after 4 seconds, way up here at the top, it's for a moment not going to be moving at all. And in fact, if you see video of balls and things shot straight up in the air, they pause for a moment before they continue.
Wile E. Coyote pauses even longer.
Okay, but it's not going to stay there. It actually is now under the influence of gravity beginning to fall faster and faster and faster. So after 1 second of falling, we're now 5 seconds into the flight. It's going 10 meters per second. After 2 seconds of falling, it's at 20 meters per second. After 3 seconds of falling, it's at 30 meters per second. And the irony is when it hits the ground where the cannon was, it's actually going the same speed it was that it left.
So one of the interesting things is the sort of not to scale aspect of this. So I talked before about how he sort of shrunk this, and then he made these two be roughly the same length, and you could tell that he was sort of trying to get down here at the bottom. And so there's a scale problem here, but I don't think that's the point. The point is all about the speeds, and so really I think he's trying to drive home, look, 4 seconds up, 4 seconds down, because if you keep chewing 10 meters per second out of this every second, 4 seconds up, 4 seconds down. So I think that's the really important point. I think he's doing such a great job with that.
40 meters per second. Bam, when it hits the ground. So that's a flying object going straight up. Most flying objects aren't going straight up though. Let's imagine that you kick a soccer ball, and we have a lot of you ladies on the soccer team, right? We were talking the other day about that. And so the soccer player, okay, one of our lady soccer players, is trying to kick the ball into the goal. Okay, there's the goal. All right, and so she starts over here, and hopefully from wherever she is, okay, here's our soccer player lady here. All right, she kicks the ball, and it goes like that. And you go, huh, so what's happening along the way with that? Well, we can take this curved line and think of it as a series of straight vectors. Because like when she kicks it, there's a certain portion where she kicks like this, and a certain portion where she kicks like that. Okay, and so as it goes up, okay, the force going up is being diminished, or the velocity going up is being diminished, because gravity, of course, is doing what gravity does. Gravity is pulling down. So this arrow gets to be less and less, while this arrow stays constant. This little bit stays constant. Okay, now at some point after that arrow flips down, because now gravity is pulling it down. It's going forward at a constant speed. This arrow here stays constant, but this arrow here gets larger and larger and larger until hopefully at some point she hits the goal. Yeah, okay? So we see the transformation of this constant forward force, but then the gravity pulling and reducing the acceleration, or reducing the velocity upwards, and then eventually flipping the velocity downwards as the ball goes like that.
So what I was watching for just right at the end there is, this one was drawn just a little bit small. And so I'm sure, I was kind of watching his eyes. I'm sure he was looking at that, right? And trying to decide, do I say something about it or not? But there's a big story he's trying to tell here. And I think that he's doing a really great job, and his language is consistent, and he's really driving the point home. But it's so interesting, right? As we reflect on how we react to things, if this were me, I'd just be staring at that, and I'd be like, do I fix it? Do I say something about it? If I say something now, am I going to lose the thread? Are they going to lose the thread? And I think that, I don't know, I really do think that he stared at it a couple of times. I was looking carefully at his eyes. But I think that he just kept the narrative thread going, and I think that was really, really great.
And any experienced soccer player knows you can actually really play with this. For example, if we imagine you're going to kick on goal here, okay, but which way, whoops, dropped my fan, hold up. How's that going to work?
I'm actually going to stop it right there. So I think that there's a lot of really cool things going on here. Number one, just the work that he's putting in to help his students from afar. It sounds like he said hi from Atlanta. His lanyard actually says Google Developer Conference, so that's actually pretty cool. And he said something about how the broken technology at the beginning. And so this is just such a great. Well, you know what? I'm just going to do this and see if it works. And look, it really did work well. And I think that I really loved how he was picking on very particular aspects of this projectile motion and really trying to drive it home. And I think where he's going to go is that, from the very same point, you don't have to have this exact shape. You could have a taller parabola or a much shallower shot. And there's so much you can pick apart with this. And I think this video is going to be really great for his students. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.